With the recent advancements of data acquisition techniques, the compression of various 3D animation data has become an important topic in computer graphics community. In this paper, we present an adaptive spatio-temporal segmentation-based technique for the compression of 3D animations. Given a mesh sequence's input, we first compute an initial temporal cut within a small subsequence to detect the dynamic behaviors. Inspired by the kernelized canonical correlation analysis method and its successful application to semantic temporal cut for motion capture data, we formulate the initial temporal cut to a maximum mean discrepancy problem. Finally, we can obtain a boundary frame for the initial temporal cut by taking the minimal of the MMD curve. After the initial temporal cut, we continue to compute the spatial segmentation based on the dynamic behaviors of different vertices. We first compute the maximal edge length change for each vertex pair. Then we conduct a binary labeling to label the vertices as deformed or rigid based on the deformation level. Based on the binary labeling results, we merge the topologically connected rigid vertices into rigid regions, which become initial spatially rigid clusters. Finally, we classify the rigid clusters to the groups with optimal internal affinities, which facilitates to exploit the spatial redundancy towards better compression performance. In our method, we propose a temporal segmentation, which determines 4 possible types of the animation block to be processed by encoder. Type 1. None of distinct behaviors has been detected at the initial temporal cut step. Type 2. This spatial segmentation has been conducted and a temporal segmentation boundary has been detected. Type 3. The spatial segmentation has been conducted and a temporal segmentation boundary has not been detected within the maximal possible range. Type 4. When Type 3 happens, we can directly reuse the previously obtained spatial segmentation to compute the temporal segmentation. Finally, we conduct abundant experiments on different types of 3D animations. As can be seen in the videos, given the maximal possible range of the initial temporal cut and the temporal segmentation, our method is able to automatically determine both the optimal number of temporal segments and the optimal number of vertex groups for different dynamic behaviors for all the data. In this way, our method can exploit both the optimal temporal redundancy and the optimal spatial redundancy for 3D mesh animation compression. These videos show the heat map visualizations of the reconstruction errors by using our method and the other methods. Overall, our method can achieve smaller reconstruction errors with lower BPVF for the experimental data. As can be seen, high reconstruction errors occur randomly on the mesh using the adapted soft. As this method is based on a linear prediction coding, which does not explicitly constrain the spatial affinities. For the adapted PCA method, high reconstruction errors occur in the regions of vertices with rapid movements. By comparing to the offline methods with the cloth data, the original soft method behaves with similar symptoms as the adapted soft method. The original simple returns high reconstruction errors on the tabletop region because this method groups the vertex trajectories based on the entire mesh sequence. In addition, our method is significantly faster than the original soft and the original simple. Our method consumed 17 seconds. The original soft consumed 36 seconds. And the original simple consumed 4,622 seconds.